So today we're going to talk about residuals. So let's see what is residuals. So residuals is basically another name for the error estimation, error in the estimation. If you remember last week we finished our discussion by talking about estimation. We talk about linear regression, then we talk about different names that it has, how you can look at the basically residuals or error in the estimation and define or draw your line based on that. So today we're going to look at that more closely. So error is basically the actual value that you have minus the estimated value that you're estimating based on the data. So some error are positive, some are negative. If you remember, when you draw the regression line, some of the points in your scatter plot is falling above the line, some of them are falling below the line. So you want to get some of the errors as negative, some of them as positive. So you can use basically these methods to measure the rough size of the errors, the one I'm going to say. You can get the square of the errors to eliminate the cancellation because they are positive and negative. Then take the mean of the square error, take the square root to fix the units, and you will end up with having root mean square errors. That's what we finished last class with. So we saw last class that we can use these root mean square errors to draw our basically, or to calculate our estimation, or to have our regression line. So as I mentioned, residual is another name for that error estimation, error in the estimation. So it's error in the regression estimate, and one residual corresponding to each point in X and Y. So you have this line of the regression line, one point is here, basically this is your, for this point in the X, this diffraction between your point and the real, basic between the actual point and your estimation would be considered as that residuals for that particular point. So residual is basically is observed Y minus regression estimation, estimate of Y, the one that you see. Or you can see it as observed Y minus high of the regression line at X, or vertical difference between point and the line. So these are all the same things, okay? If you consider the line, the vertical point between this point and this line is your residuals. If you have the observed Y, you can calculate your high of the regression line at that point in the X-axis, then that would be your diffraction, Y would be your residuals. Let me show you in the code, it would be much clearer. So if you just joined, we just started, you didn't miss anything, we were just reviewing last week class. We were talking about residuals, which is another name for error in the estimation. So here I'm defining all the functions that we saw before redefining them to use to convert the standard unit, to calculate the correlations, or R, to calculate the slope of my line, to calculate the intercept, and to have my basically fit value for that, or the predicted value, which returns the high of the regression line at each X value. So I have all this function I'm going to use. Let's look at Little Woman table, the one that we saw last week. Basically, it has all this 47 chapters. And in each chapter, how many periods you have versus how many characters you have. So, and this is the table for shot put. I'm going to just load them, then we're going to look at those tables. The shot put was that sport that you have this big metal ball that you have to throw. The longest you throw, basically, better result you get. So this is the scatter plot of Little Woman. I'm looking at the periods versus characters, and I put that fit line, the regression line. So you can see some points are about basically a regression line, some of them below. These are things you already know. But the point is, if I add all these residuals, okay, now you know what is residual. Residual is this y value, the characters, minus the fitted value, which is this line, the values that falls in the line, right? Those are my estimation. So that's my residuals, or basically the error in the estimation, this line, if I try to annotate. So this is for example, for this line, this is my residual. For this
Si los
line,
quería cachar puercos.
For this line, this is the residuals. For this line, this point, this is the residual. For this point, this is the residuals. So if I add all these residuals, what do you think I'm gonna get? What value I will get? If I sum all of them, there are some of them positive, some of them negative.
Something close to 0?
Exactly, it's basically exactly 0. Let me clear. So if I calculate it here, I put, let me, before running this, I put draw my residuals. So these are the residuals for all these points, for all that 47 chapters. You see some of them are positive, some of them are negative. So I want to get sum of this. So if I get sum of it, you see this number. But if you pay closer attention, you see this is this number to the power of minus 11. So this is pretty, if I do that round, you can see this number is basically 0. Okay, if I round it, I get 0. But you know, the Python show it in slightly weird way. So if you add them, all of them, you get 0. And this is our root mean square error, right? You know how to calculate this. This is that basically root mean a square of these errors. That's our RMSE, or root mean square errors. That one we were trying to minimum. You remember last week we were saying another way to do that regression line is calculating the minimum root mean square errors. So but let me, what happens if I plot these residuals? Okay, this plot shows what I'm doing here. I'm plotting how to say the residuals for, if I remove this. So this is my little woman table now. I add this residual value here. So these are the period, these are character, this is the residual that I already calculated here. So if I scatter plot this, I'm going to get something like this. So if you can see here, this is the 0 one. Basically what it means, this 0 line is, for example, these two points are pretty close to my fitted value or to my regression line. The farther we go, is the farther points, basically. Those close points are, for example, these two are the farther point you see, you get a bigger value. And you see some of them are above it, some of them are below it, and I already show you that if you sum them up, sum them all these values, you get 0. So you see, there was a pretty close linear how to say relationship between these two characters, between these two periods and characters, right? You can see it's pretty close. So for something like that, you get a residual plot of like a cloudy scattered data. Okay. So one of you, I don't remember who was that exactly, asked me how, I think on Damaso was that, how we can know what we use. Okay, like we use linear regression or we use nonlinear regression. So another way to find out about that is looking at that residual plot. So you get something like this for those values that have linear relationship. So you get something like this, cloudy dots. Okay. So let me put that in a function. So I want to call the same function for the shotbot data. So you remember in shotbot data, we saw first last week what we did linear regression, right? Then we saw, okay, maybe these outliers data show us maybe nonlinear equation would be much better fitting this table, these values, association between these two values. So that was what we saw. So this is this basically functions draw these two scatter plot, one with the how to say the regression line and one with the residuals. So this one give you these residuals. So this is your zero value, okay? And if you draw this residual, now if you basically plot this scatter plot for the residuals, calculating from the shotplot, you can see it's different with what we saw for a linear relationship here, which is this. Here for shotplot, we see this. Again, we have this very far outliers. So basically looking at this, it can help you a lot with deciding you can go for linear regression or not. Let me go to the slide. So talking about the residual plot, it's a scatter diagram of the residuals. So it should look like an unassociated blob of linear relations, the one that I show you, but it still contains pattern for non-linear relationship, the one like, for example, for shotbot. So it can be used to check whether linear regression is appropriate for some data or not. You already saw that. So let's talk about more about regressions, properties of regressions, the diagnosis. So we're going to look at dogong. Dogong is the name of this animal. We're going to look at these tables to see what we can find. So this is a table for dogong. What it shows you, it's the age of the dogong and the length of dogong in different basically part of the life. Okay. So how old is it and how tall the dogong can get in a certain age. So if I draw the residual plots, basically the plot with, this is the regression line, and this is the residual plot. Okay, so you can see again for this particular table, for dogong table, R is pretty high, right? R is 0.8, which is, you remember when we said when R is, the closer R is to 1 is, you have an upward linear relationship, to the -1 you have downward linear relationship. R0 means there is no linear relationship between these two values. So you can see here the R is pretty high, it's 0.8, and root mean square error is this. But if you look at the residuals, you can see not that blob of unassociated data point that we can see, like for this one, for the little woman, periods and number of periods and number of characters. So you see a slight pattern here, something like this, a curve, okay? So that might make you wonder that if this linear regression line is suitable for this data or not. Let's look at another table. So this is the US woman table. So what it is the average of woman height in the United States. So what they did here is they get, for example, if a woman, a lot of women with the height of 58 inch, with the weight of 115. So the average weight, those are that around that they're 58 inch tall. The average weight of them are 115, and all the way along, you can see. So if we do the correlation here, you can see it's close to 1, okay, which means it's like almost a perfect linear relationship between these two values. Are you following up, or you get lost? It's clear what you're doing? So I'm calculating the correlation. I'm showing you there is a high correlation, okay? So if I now draw this two, this one, I'm fitting the regression line. You can see it's fitting pretty close, right? Because the correlation coefficient, or R value, is pretty high. It's close to 1. But when I draw the residuals scatter plot, I see this. This is my 0. So what can you tell me from this to the scatter plot? Anyone can comment on that? Anyone? George, name? Umberto, what do you think?
I don't know.
Anyone can add? Ricardo, Daniel, you there?
Since the scatter plot is showing that the how was it called, the error follows a pattern, it suggests that a non-linear approach would be better.
For here, so you mean because this residual plot is showing a pattern, so non-linear approach will be better?
Yes.
So, I mean, I let that for you to decide about it. But yes, true. I mean, you can see here, it's look like linear, but if you pay more attention, it has a slight curve. Okay, so that's why we see this pattern in the residual plot. So you might try to fit a nonlinear equation to this, and most probably you're gonna get better results. So I have another question for you. Okay, for example, here, looking at height, I don't know, let's say 70 inch, and I get this point from my regression line, I get this point on 155 average weight. So can I say if a US woman is around height 70, is around 70 inch, has high of 155? Can I conclude that?
What was the last part? Sorry.
The question is, can I conclude from this regression line that I draw for this data that if the woman height is 70, so with a good estimation, she's around 155.
Oh, sure. I think you do. You can.
Who says I can do that? Who says not? I cannot do that. So everyone agree? So you remember last time we were talking about the points that you need to take care about linear regression line. It's like ecological correlations. You remember we were talking about ecological correlation, those correlation that you get, you average different people's data, and you draw the mean of those data, like what we are doing here. This table showing me a lot of women in this height, the average weight is this. A lot of women in this height, the average weight is this. A lot of women in this height, the average weight of them is this. Maybe 5 of them are 130, 5 of them are 110. You get average, you end up with 120. So from this table, you cannot conclude anything for individual persons. So those are the things you need to really take care of, especially that ecological correlations. Those data that are averaged, those are average, so you cannot conclude for individual person. So just a review on what we talked last time. So let's go back. Let's talk about the properties of residuals. So we want to talk about residual variance. The mean of residual is always 0, the one I show you. If I add all the residuals together, I'm going to end up with 0 because some of them are positive, some of them are negative. The whole point of that regression line is to go exactly through all the lines, all the points in my scatter plot, in my data. So definitely some of them going to fall up, some of them going to fall down, but averaging them, all those errors, negatives and positives, I'm going to get 0 regardless of the original data. So you remember this also, variance is a standard deviation squared. So mean squared deviation, this is the equation we saw earlier. So we have this properties for residual variance. So variance of residuals divided by variance of y, or the my data in the y-axis, are equal to 1 minus r to the power of 2. So from here, you can conclude if r is 1, there is no variance in residuals. It's pretty logical, right? You remember when r was 1, your correlation coefficient was 1. It was perfect linear relationship. So it means all your dot in the scatter plot fall in this line. So of course, you're not going to have any variance in the residuals. Your variance of residual is going to be 0. Is it clear? So variance of fitted value, the fitted value, remember, was basically, I have all these dots. I'm fitting this value on this regression line, right? For this particular part of the scatter plot. So variance of the fitted value divided by variance of y is equal to R2. So from this, you can conclude, what you can conclude from this? If R is 0, there is no variance in the fitted values. Is it clear? It's a pretty rational conclusion, right? Because if R is 0, this is the R0, right? So there is no variance on the fitted value. All the fitted value in a y-axis falling in this 0. So there is no variance in the fitted value when R is 0. So there is another equation, is like invariance of y is equal to variance of fitted value plus variance of residuals. This is also pretty straightforward. Any question about this? We're going to, is that clear? So let's look at some demo. So this is just a function that I'm going to, just a demo for those rules that I show you. So here I have this scatter plot. Okay, and I'm going to vary basically my R and see how it changed. The variance of residuals divided by variance of y, variance of fitted value divided by variance of y. Variance of y is 1, variance of fitted plus variance of residual is 1, and those are just not rounded. So if I go towards 1, in 1, when my R is 1, so my variance of residuals is 0, because, for example, in R0, you see all these black dots, my data. So in 1, you don't see anyone, because actually they are there, but just below this blue line. So because they're all falling in my regression line. Because R is 1, so there's a perfect relationship. So there's no variance on the residual. There's not one of them up, one of them down. There's no variance. So variance is 0. So variance of residual divided by variance of y is 0, and variance of fitted divided by variance of y is 1. So if I go all the way to r minus 1, you can see exactly the same thing again. So variance of residuals is 0, variance of fitted divided by variance of y is 1. So what if I go to, for example, point y? So you can see how it's changing. For example, in R.5, variance of residual divided by variance of y is 77, variance of fitted or variance of y is 26.026. Is that clear? So this is coming from the previous equations that I show you here. Okay, so this is helpful sometimes. I'm going to talk about it when it comes handy. Here, basically, you can get some basically, how to say, how can I? It will be handy later. We'll talk about it with some example. But you just remember this is not that complicated. If you remember, if you can imagine the scatter plot with the regression line, you can know what we're talking about variance of residuals, variance of y, variance of fitted value. So these are pretty straightforward relationship. So is there any questions so far? If no, so you answer this question. So which one is correct? A, B, C, D? Oops. I'm gonna try this. So you don't see the question?
No.
Okay. Yeah, okay. It's here. Here it is.
Thanks.
This is I'm just trying to see what is this Zoom for, how it works. Okay, we are missing 20 people voting. Maybe I shouldn't show you because it can affect your judgment. So there are 7 people missing. Can you just vote based on what you think? No more voting? Okay, let me see, I can see the, okay, this is what I got. Not, it doesn't mean this is correct, I forgot to fix it, okay? This is not correct, okay? So you remember last slide I showed you what we were talking about, the variance, right? Variance of fitted value divided by variance of y, variance of fitted value divided by, you know, let me show you again. This is what we were talking. Variance of residual divided by variance of y, variance of fitted value divided by variance of y. Okay? So, you know, variance, or basically a standard deviation is a square root of variance. So basically here, what you're doing for the next slide here is you're getting the root, a square root of all the equations, all the parts. So you end up with a square root of basically variance of fitted value divided by a square root of variance of y equal to absolute value of r. Basically, this is the correct answers, B. You got it? Why? Any questions so far? Okay. So yeah, so this is the correct answers here. The B, option B. So let's talk about regression model, how we can model the regression. You remember this is considering this is our regression line. We have this scatter plot. We saw that's what we were showing. We have this scatter plot that can come from our population or our samples from the population. We get some points and we draw the regression line because we think there is a linear regression relationship between them. So so this basically this is the distance drawn at random from normal distribution with mean 0. So if we consider this is the case, then this distance should follow the normal distributions. So it means that I should have more points closer to my regression line than farther from them if they are following the normal distribution with mean 0. So anyway, from this, what I want to tell, we have this prediction, okay, this model, we have the signal, and we have this noise of basically our residuals, which are the distance between our actual value and our regression line. But this is what we see, right? This is what we get to see when we are drawing a scatter plot or we are collecting data, we're sampling, this is what we're going to see, right? We don't see this. We're seeing this scatter plot. So let me tell you what I want to highlight with this. So, okay, let me see what. So imagine this scatter plot. Okay, this is the actual line fitted to this scatter plot. Okay, this is imagine I draw my scatter plot. I draw the line. Okay, but this is what we see, right? This is what we get to see, this scatter plot with like 10 points inside. Okay, and this is the actual regression line. This is the actual regression line from my population, let's say. Okay, but what I wanna, let me correct myself what I'm trying to say. This is the samples. Okay, I'm sampling, let's say, my population. I draw my regression line. This is the actual data. This is the original regression line. Okay, this is estimated up to true line. And this is the earlier line that I draw. So we always get some, how to say, some, how can I say, some error in our prediction, right? Because we don't have all the actual line from my population. Here I'm talking about sampling, okay, the line from my samples and the line from my original population. So this is the actual regression line for my original population. The green one is the one from my sample. Sorry. Let me show you another example. Here, what I'm doing, what I did here, I'm taking 10 samples. As you can see, I have 10 samples. I draw my regression line from the samples. Then I see this, and I get this error. The dark blue one is the actual regression line from my population. The green line is the one that I'm predicting from my sample. Is that clear? So I took 10 samples. What if I took 100 samples? So here I did 100 samples from my population. I draw the regression line for that 100 samples. Then this is the actual regression line from my population. And this is basically here in this figure, you can see next both my prediction and my actual line. So the idea is we're always going to get certain errors because we are sampling from the population. We are not having the exact regression line for the population because we can just sample. This is the one we are talking all these last sessions. So we get always these errors. So if I increase the number of samples, this is what we were also discussing at some point, that how big my sample should be. So if I increase my number of samples, this is the samples I got, this is my predicted regression line from my samples. And if I put them next together with the actual regression line from the population, I get pretty close to the actual regression line. So what if I increase my sample to 1,000? So this is 1,000 samples. This is the actual regression line from the population, and this is the regression line, the predicted regression line next to the original or actual regression line from the population. So what I'm trying to say here is, by all this, is there is an error depending on how big is your sample from the population. You want to get some errors, okay? Because if you take a small samples, okay, then your regression line is not going to really represent your populations. So if you increase the population size, you get if you increase the sample size, you're gonna get much closer to actual populations. So that's what I'm trying to demonstrate here using the regression line. Is that clear? Any questions so far? Okay. If no, let's talk about data slope. So this is what we're going to talk about, the true slope, or how close is our sample slope to the actual slope. Because anyway, we don't have all the population data. That's not the case. We don't have that leverage. We can only have the samples. So we want to calculate how close the slope of our sample is close to the actual population slope, or let's say true slope. So you remember we did that, for example, when we were checking all the public San Francisco workers, that table, that we had all the pupils, like 30-something thousand data, and then we were sampling from that table, like 200, and we were trying to predict what is the average income for that population. So for that example, we use these confidence intervals. If you remember, we used bootstrapping method for calculating that. So we can do the same thing for the scatter plot. We can bootstrap the scatter plot. So we bootstrap the scatter plot, we find the slope of the regression line through the bootstrap plot. And then we repeat this process, exactly what we did with that public San Francisco workers, trying to predict the average income. Now we're going to do the same thing with the scatter plot. We repeat this process, we draw the empirical histogram of all the generated slopes. And we get the middle 95% of that interval. That would be our basically approximate 95% confidence interval for the slope of the true line. So a simpler way, you remember this is, I show you, for example, I take 10 samples, I'm gonna get different type of slope. If I take, so what I'm gonna do here, I'm gonna go to my population, I'm going to sample, now I have the sample. So basically, if you remember, bootstrapping was resampling my samples. So I'm gonna do the same thing with the scatter plot. I'm gonna sample, draw the scatter plot, resample from my sample, draw the scatter plot, do the regression line, calculate the slope, and then draw the histogram for all this data and see what we get. So you remember this table? This is that table, baby table, that has all this value: baby birth weight, gestational days, how many days is the baby in the womb, maternal age, maternal height, maternal pregnancy weight, smoker situation. So we're going to look at the relationship between gestational days and birth weight. So what I'm interested to see is if baby stays in the womb of the mother for a longer time, is the baby going to have a bigger weight or not? That's what I'm going to basically, that's what I'm interested to find out. So if I draw this two table, the first one is basically the scatter plot with the fitted line, with the regression line, and the second one is the residuals. So you can see there is this R is 0.4. There is some linear relationship upward, some positive linear relationship based on the R that we calculated. And this is the root mean square error. And you can see here, this is the 0, 1. Those lines are close to my regression line, the other line are farther away. So if I calculate the slope,
Lo que pasa es que no sé si le haga falta oxígeno.
any question? Laura Augusto?
No, it was a mistake.
No worries. So here, what I'm trying to do, I'm calculating the slope for my regression line. Okay, this is the slope of my actual data, right? From all this data that I have. So what I want to do is I want to sample from this baby table and then scatter plot and fit the line. And I'm going to do that 4 times using the slope. So here I sample the first time, sampling from the baby table. I draw the regression line. So you can see, for example, between this regression line and this regression line, if you look at this point, maybe you can see the difference because there are 2 different samples from that table. So here I get this regression line with different slope. I get the second sample, I get this regression line with this slope. For the third sample, I get totally different slope. As you can see here, the slope is, this is not a slope, this number. I'm just pointing for you to see the difference. The slope is the angle, basically, you can consider that. So you can see I run it 4 times, I sample it 4 times, 5 times, I get 4 different slopes. So what I want to do, I want to do that multiple times. I want to do that 5,000 times. I want to draw that. I don't want to draw. I'm going to calculate, sample 5,000 times from my baby table, put all the slopes in my slope table, then to see what we can do with that. So basically, this is the bootstrapping for this, the same thing that I was talking. So let's see what we get. So we get this histogram. So I want you to look at this histogram and tell what you conclude from this histogram. or what the histogram is telling us. What does it mean, this histogram? Anyone? Any idea? Xian, can you share with us what does this histogram is telling us?
I don't really know.
What I'm doing here, I mean, don't get confused. It's like pretty straightforward. Okay, let me talk about this slope that I calculate here. What this number is telling me? The slope the slope of my regression line between gestational days and birth weight. So what I'm trying to do here is like to predict my birth weight based on the gestational days. How many days is baby in the womb, and based on that, what would be the weight when the baby born? So based on this regression line, I'm saying, okay, for example, if I'm in 250 days, the baby is in the womb, I'm predicting the baby weight would be in this regression line or somewhere around 110 pound, right? No, I don't know what is the unit here. So what I'm saying, for gestational day of 250, I go to my regression line, I see this is my fetal value, so I predict it should be 110, the baby weight should be 110. For 350 days, I'm predicting the baby weight should be 150, somewhere around that, right? So this slope, what the slope tells us is like for every single extra day that the baby is in the womb, the baby going to get this much more weight, 0.4. Or if the baby 10 days if the baby is, for each 10 days, extra 10 days that baby is in the womb, it's going to get 4.6, I don't know, let's say ounce. So that is the slope. That's why the slope telling us. If I annotate, or yeah, okay. You remember the equation was like y equal to I don't know, whatever, a multiple rx plus b, right? That was this is basically our linear equation. So S slope is a is the slope. This is my x value. My x value is basically gestational day. My y value is residual. Sorry, not residuals, but let me undo it. My y value is birth weight. So this is the equation I'm trying to calculate here, right? I'm doing exactly the same thing. I have this x, my gestational day. I have my slope, which is this a, and I have some interceptor. So is that clear? So now what I did here is, I did this slope. I calculated the slope for 5,000 samples from my table. And I get this histogram. So based on this extra explanation, can anyone tell what does it mean? Come on, someone should have some idea. Ricardo, Daniel, you're quiet. Anyone? Jose Chosa? I'm just randomly asking from the names
It's
here.
all of the 5,000 slopes you calculated.
Uh-huh. Yes, so what you can say with this? Yeah, I calculated 5,000 slope and I put that in a histogram.
Well, based on the bootstrap concept, it means that the population, the slope population, it's pretty close to 47.47,
Mhm.
48.
Okay. So, okay. Yeah, you're close, Diego. You almost got it. It's, you remember when we were doing this histogram and we were, I didn't put the, I'm going to do that later. I didn't put that confidence interval, but what I'm telling here is, okay, let me show you this. If I cut the 2.5% in the left and 2.5% in the right to get my 95% confidence interval, so it means by 95% confidence, I can say each extra days that baby is in the womb, the baby going to get like 0.38 to 0.55 ounce more on the weight. Is it clear? So that's what we are doing here. This is the same thing we were doing for the income. For example, we did the income, we said, okay, for example, the average income is with 95% confidence is like the average income for my public workers in San Francisco is between 95,000 to 97,000, right? That was we were doing. So now here we are doing the same thing. So this is basically the slope, using the bootstrap slope for the table. And why we are doing this? Because not necessarily we have access to this value. This value. This is from my population. Okay, this is from my population. Let's say the actual. If I consider this is not even my population. This is just 1,200 people, right? But there are millions of other people. So let's say this is a sample. I'm doing this sampling, resampling 5,000 times. I'm doing that to come up with this confidence interval. And with this confidence, I can say one extra day baby is in the womb, it's going to gain this much weight, this much extra weight between these two days. So I'm gonna put the same thing in basically the table functions to call it. So this is the same thing, baby weight and gestational days. And another is maternal age and gestational day. So this is the same thing, I just wanna draw the confidence interval on top of it, make it more clear. Is there any questions so far? Or are you following up? Are you getting what's happening? If there is really a question, ask. I can clarify it further. When you don't ask, it's like it's worrisome, you know. That are you getting what I'm talking about? Are you getting what's happening here or not? So this is the same thing. I put this function. So this is the slope of my regression line. This is my approximation of 95% confidence interval for the true slope. So this is the true slope. I say by the, this is the basically between these two numbers. As you can see here, by the golden color. So I put the baby table. So you remember what was that? So this was the baby table. So now I'm interested to see if there is any relations between maternal age and gestational days. This is my maternal age and gestational days. So let's do that. Let's see what we get. So this is that plot, the scatter plot with my regression line. Then I fitted my regression line, and this is the plot for the residuals. So I'm just putting them so you can see how it's working. So R value is minus 0.05. It's very, very small, but it's not zero, okay? You can see the slope downward not zero, but it's very slight slope downward, right? So you might, based on this, you might say, okay, my R is not zero, so there should be a slight, pardon, Carol? Carol, you have a question?
No, sorry.
Okay, no worries. So this is the slope I'm seeing. It's a small slope. So before I show you the next one, let me see. So we observe a slope based on our sample of points, right? But the question is, what if the sample scatter plot got its slope just by chance because I'm sampling, right? I'm going to my population, I sample, I calculated my slope for my regression line. But what if that is just total by chance? So what if the true line is actually flat or different, right? So that's what we're trying to do. So let's talk about how we can find out about that. So we can use now our hypothesis testing. So the null hypothesis is the slope of the true line is zero for that particular example that I show you. Alternative hypothesis is no, it's not. So the method is I'm going to construct a bootstrap confidence interval for the true slope. Then I'm going to see if the interval doesn't contain zero. Then I can reject the null hypothesis. If the interval does contain zero, there isn't enough evidence to reject the null hypothesis. Any questions about this? Do you remember this hypothesis testing? So okay. Pardon?
So even if the number is very, very small, you're still going to reject the null hypothesis.
If it's not zero, I'm going to reject the null hypothesis. It's tricky, okay, but I'm going to talk about that example because it's pretty close to zero. So, but anyway, I'm going to do the hypothesis testing. I want to see if the slope of the line, the true line is zero. Even if I don't get zero, if I get 0.1, it still is not zero. I can, I mean, scientifically, I can conclude something based on that. Though it's close to zero, it's not zero. So there should be a slight linear correlation between these two values. So this is my hypothesis. I'm going to test it between, you remember, between gestational days and maternal age. So let's do that using this bootstrap method that we saw. So what I'm going to do here is like, I'm going to 5,000 times repeat this process, sampling, drawing, let's say, the histogram, calculating the slope, putting that away, another sample slope, and I'm going to end up with 5,000 slopes. Then I'm going to draw the histogram for that. So this is what we get. So what can you say from this? Should I reject the null hypothesis? The null hypothesis was the slope of true line is zero. So this is the zero. And alternative hypothesis was no, it's not. And I wanted to say if the interval does contain zero, my 95% intervals contain zero, then I can reject the null hypothesis.
I think that even though we have like a very small number of our parameters at a 95% of confidence, we cannot have the enough evidence that we can reject the null, because even the slope is very slight. There is a slope and we can reject that, at least with that parameters.
So the thing is, now my, yeah, exactly. But now 0 is contained in my 95% confidence interval. This is 0, right?
Oh,
So
yeah, I'm
it-
sorry. Yeah.
So 0 is inside my 95% confidence interval. So based on this, I cannot reject null hypothesis. My null hypothesis was the slope of the true line is 0. But now I see, no, I cannot reject null hypothesis. Because 0 is there, right? 0 is in my 95% confidence interval. So maybe if I increase my confidence interval from 95 to another value, the 0 going to fall out, but, or of course that's going to happen. But in this 95% confidence interval, we can say there is not enough evidence for us to reject the null hypothesis, even though the number is pretty small. Is that clear what we did here? Okay, I hope it's clear. So we can do the same thing for what we did for the slope. We can do the exactly same thing for predictions. So we can do that, calculate the variability of our predictions. I'm not giving any pause or break because we are almost there, okay? So let's just continue. So for regression prediction, what we can do is, if the data comes from the regression model, the regression line is close to the true line. So basically, what if our sample is large enough, it is close to the population, it is close to our actual value. If I take my sample large enough, it's going to be close to my population. So given a new value of x, predict y by finding the points on the regression line at that x. Bootstrap the scatter plot, get a new prediction using the regression line that goes through the resample plot. Repeat this two-step above many times and get an interval of prediction of y for the given x. I think it would be much clearer what I'm saying here, because the whole idea is here, the same thing that I did for the line. I'm going to use the bootstrap method to calculate, to know my predicted value or my fitted value. So this is the same thing, okay? Gestational days and weight. So this is my scatter plot. I put the regression line there. So this golden line, what I'm trying to say here is like, I'm going to look at this point for gestational 300, gestational days 300, what would be the birth weight? Based on this, what I can see here, that the point that touches the regression line is around 130, right? Let me see. So it's 100 to 9. Okay, this is my fitted y, right? You remember this is how we calculate. This is my equation, my linear equation. A multiple. A is my slope, B is my intercept. And here, slope and intercept, I already defined the function to calculate this slope, the intercept. This is my fitted y now. So for this 300, the gestational day 300, my fitted y is around 130, 129. It's around here. So I want to do that for different lines. So this is from if I consider this is from my population. So what I'm trying to do here is now to sample, okay? What I'm doing here, I'm sampling. I'm not showing basically the scatter point, the data. I'm just showing the 300 day, okay? My prediction, my fitted value, and the regression line based on that. So this is based on one sample. I do one sampling. I have all the samples, let's say here, the dots that I didn't show. This is my predicted, my fitted value, and this is my regression line for that one sample. But what if I take 10 samples? So this is my fitted value for that 10 samples. I sample one time, I get this value, I draw the regression line. I sample another one, I get this value, I draw the regression line. I'm not showing that dots. I get another sample, I got this fitted value, I draw the regression line. So you can see if I do that 10 times, I'm going to get 10 different points. Is it clear? Because I'm sampling from my data. Then I draw the fitted value, I calculate the fitted value and the regression line. So if I do that 50 times, I'm going to get 50 different points. If I do that 100 times, I'm going to get 100 different points with their own regression line, because I'm getting 100 different scatter plot here. I'm not showing, I'm just showing this fitted value on 300. So what we can say here, what we can see here is like for this 300 gestational day, the birth weight falls between, let's say, I don't know, 131, let's say this one, top, all the way to 127, between these 2 points, right? All the way from here to here. So that's what exactly I mean. So I want to do that same thing here using the bootstrap method to calculate, to say by certain confidence interval, okay, so I'm doing all of them. So by certain confidence, I can say my prediction for my y value is falls in certain range. That's what I'm trying to do. Because each time I sample, I'm going to get different prediction for my fitted value. Is that clear? Any questions about this? No? Okay, so let's see what we got. So this is for the table, baby table, gestational days and birth weight for gestational day 300. So I get this histogram. Now, can anyone tell me what this histogram is telling me? One of you guys can tell what does it mean, this histogram? What is showing me?
It shows that, well, I believe that it shows that if the gestational days are 300 exactly, the birth weight will be between 127.25 and 131.31 with a 95% confidence.
That's precisely what it's showing me. So what it's showing me exactly, as David said, is in gestational day 300, by 95% confidence interval, my birth weight is going to fall between 127 to 131, this period. Is it clear what we're doing? And the width between these two numbers is like 4. Okay, my basically preciseness is like 4. And let's look at this table again, 300. So I'm looking at here, right? It's 300. This is not exactly around my mean. My mean would be somewhere, I assume, around 280 days, somewhere around here. So the thing is, the more I move farther from the mean, it would be harder to predict, right? If I, for example, try to predict for gestational days 250, I don't have much information there. I don't have much, let's say in this case, I don't have much point there that I can have a good prediction for gestational day of 200. I just have one close here, maybe 2, 3 here, one here that is not even close. But I don't have enough information to do a good prediction for my gestational day 200, not even for gestational day 350, right? So let's say, let's try that. Here I'm doing the same thing, okay. I'm moving to 330. I'm moving here. I wanna calculate for this value, this point, okay. So you can see there's way more less data here. So if I do all the bootstrap method, calculate my 95% confidence interval, I'll get this. So what it tells, again, by 95% confidence, my data and the baby weight for gestational 333 days going to fall between 138 to 147. So you can see here the width of this duration got larger because my preciseness is dropped, because I cannot be very precise because I don't have much information there at this point to predict, to have a good prediction, right? That's why these two numbers are very far from each other. So what if I get closer to the center, somewhere around my mean, which would be falling in 280? See, if I go there, I calculate the same thing again, I'm going to get this. So again, by 95% confidence interval for gestational day 280, the baby weight is going to be between 118, around 119 to 120. So the width is just 1.8. So you can see I can predict much more precisely here, because in day 280, gestational day 280, I have a lot of data to predict based on all those data. Is that clear? Any questions? Doubt? So all thing I did here, try to do the bootstrap method for my prediction. Prediction is basically my y value. Based on x, the number in the x axis, I'm trying to predict my y axis. That's my prediction. So here what we did was, I was trying to calculate the slope. Is that clear? So since y is correlated with x, the predicted value of y depends on the value of x, obviously, because there was some correlations. We calculated r was not 0. That's why we can consider this. So the width of the prediction interval also depends on the x. So we saw if we go to the part that there is not much data, so we don't based on this, we don't get a good precise prediction for our y value. So typically intervals are wider for values of x that are further away from the mean of x, as we already saw in those examples. Because the farther you get from the mean of your data, the less data you have, the prediction would be wider. For example, I say I guess based on this 330 days gestational day, my prediction would be way more wider than my 280 days in that particular example, because 280 is closer to my mean of data. So to recap, linear regression only gives us one estimate, but bootstrapping gives us multiple. From one sample, we can get confidence interval for slope and predictions, for different slope and predictions. So there is this library, Seaborn. What it does, basically, it does exactly whatever we did automatically. So it draw your histogram, it draw your regression line, and calculate your 95% confidence interval. So this, the dark blue one is your regression line. That shadow here is the regression, the variance of the slope for your regression line. So you can see just based on this, it's pretty nice, pretty handy. Based on this, you can see the farther you get from the mean of your data, the prediction would be wider. Closer you get pretty closer predictions. Is it clear? So any questions about what we talked? If you have question, if you didn't understand any part, it is time to ask. I mean, we are approaching end of semester. Don't let it be something that you didn't completely understood. Any question? So if basically I'm done next week, I was hoping to have time to talk about classification today, but next week we will just consider about classification, which is the main thing that we are trying to do in project 3. So a little bit of machine learning here. So, but yeah, I leave that for the next week topic. If there's no question. So if there is no question, I'm going to stop sharing. So I have an activity for you to do, but in your time, not necessarily in the class. Just let me talk about it. Okay, I'm going to, okay, fine. I mean, I got disconnected. I couldn't do all these things beforehand. Let me stop recording. No, it's, I'm going to, you need to do now lab 8, okay, on your own time. I'm going to put the deadline for end of, for Monday midnight, okay? I just do it so I don't forget that. For lab 09, that's the one. So let's put the deadline for Monday midnight. Okay. I haven't uploaded it, but right now I'm uploading it. I will upload it to the Google Drive, to the shared Google Drive. So if you're doing it locally, use the Google Drive. I will upload it to the server if you're using the server. So we are done today. If there is no questions about the activity we're going to do. Any question?
We have also a homework, right? Homework 7, I think. It's in OKPy. Homework 7.
Yes, I will upload both of them because I already covered the content for both of them. But I'll put this Monday, I'll put this till the weekend. Okay, let me do this right in front of you. So I'll put the lab one for this Monday. I put this for, let's say for Friday midnight. Is that okay for you guys?
Yes.
All agree? So
Yes.
the first one, the lab activity would be Monday midnight, the next Monday midnight. The homework activity would be for next Friday, Friday 29, midnight. Yeah, because I already actually, honestly, I cover everything for last homework and the last activity. So I upload both of them so you can adjust your own time better. That would be basically these two will be our last activities that we needed for this class. And the only thing missing is the project. But for that, maybe it would be better for you to do the second part after I talk about the classification, because that you need that part for doing that project. So if no more questions, we're done with today's class. Thank you for being patient. Thank you for coming late. Thanks for the problem.